Hi guys, today we're talking about the Pythagorean Theorem. This is something that you start learning about in about 7th, 8th grade. The actual definition of the Pythagorean Theorem reads, the sum of the squares of the legs of a right triangle is equal to the square of the hypotenuse. More commonly, we know it as a squared plus b squared equals c squared. Okay, and that's all that definition is telling you is a squared plus b squared equals c squared. Now, we do have to remember A and B are always going to be the legs, okay? And C will always be the hypotenuse. So anytime you're trying to figure out which one is which, okay, C is always going to be your hypotenuse. Your hypotenuse is always directly across from that right angle. So if you're not sure which one is the hypotenuse, they're not labeled A, B, and C. Directly across from the right angle, that's your hypotenuse, okay? So you're going to find your right angle, go across, there's your C. And the two legs make up that right triangle, okay? That's just the basics. All right, let's look at a couple of examples of how we can use the Pythagorean theorem to find a missing side, okay? So if I have a right triangle that has a side of 6 and a side of 8, okay? So a leg of 6, a leg of 8, and I'm not sure what the hypotenuse is. If I want to find the hypotenuse, I'm going to go ahead and plug it into my formula. So 6 is going to be my A, 8 is my side B. Okay, those are my two legs. So 6 squared plus 8 squared equals C squared. Okay, 6 squared is 36. 8 squared is 64. When I add those together, I get 100. And if I take the square root of each side, okay, what we do to one side, we must do to the other side in an equation. So the square root of 100 is 10. So my hypotenuse is 10. All right. This is something called a Pythagorean triple. Okay, when you have three whole integers, three whole positive integers that work well within the Pythagorean theorem and they satisfy that Pythagorean theorem, then you have what's called a Pythagorean triple. Okay. Now, if you end up with a radical still, you know, you can't completely simplify it down to an integer, then that is not a Pythagorean triple. Okay, just a little extra tidbit there. Let's look at example 2. Let's try some larger numbers because this works with larger numbers too. Okay, this time let's say we have one side that's 40. We're going to call our hypotenuse 41, and we're going to look for side A. Okay, so this one's going to be side B, and of course our hypotenuse is side C. So when we plug it into our formula, our A squared, because that's the one we're looking for, plus our B squared, and our B is 40, equals our C squared, and our C is 41. Okay. Well, when I square 40, I get 1600. And when I square 41, I get 1681. Okay. So now I'm going to subtract. So I'm going to take 1600 for both sides. And I will end up with A squared equals 81. And the square root of A squared equals 81 gives me A equals 9. So this side right here is 9. Okay. It's another example of a Pythagorean triple because all three sides are whole number integers, positive integers. Let's look at a couple more examples. So example 3. Let's see, we have one side here. This leg is going to be the square root of 15 long. This side's going to be 5 units long. And we're going to look for C. Okay. Well, right off, we know we don't have Pythagorean triple because one of our legs is a radical. It's a simplified radical. So we're just going to go ahead and fill things in. Okay, so this is going to be our A. Here's our B, and then we're looking for our C. Plus 5 squared. We have the square root of 15 squared plus 5 squared equals C squared. Well, when I square a square root, then the square and the square root kind of cancel each other out. So I end up with just 15. And 5 squared is 25. Well, 15 plus 25, I'm going to get 40 equals C squared. And now we need to take the square roots of those. And we want to simplify that as much as possible. Simplify that radical. There's a couple ways you can do this. You can do a factor tree. I like to do prime division. You can, if you happen to know your perfect squares, you can kind of go through your list and figure out what perfect square multiplies into 40 evenly, and then the factor left over goes under the radical. I'm just going to go over here off to the side and do some quick prime division. And so I have a pair of 2's. Those are going to come out, and then this 2 and this 5 will stay inside. So 2 square root of 10 equals C. Okay. Now, when we're taking these square roots, we've only been looking at the positive answers. We've just kind of said, okay, the positive answer is our answer. When we're talking about triangles, we cannot have a negative length. So for those of you wondering, why aren't we doing both the positive and negative version of the square root? It has to make sense with the context. In this context, we're talking about lengths of triangle sides, in which case all lengths of a triangle side need to be positive. So we only deal with the positive. Okay. And our last example that we're going to look at. Let's say we have side A that we're looking for. Side B is 3 times the square root of 6 units long. And side C is 9 units long. Okay. So we're going to do A squared plus 3 times square root of 6 all squared equals 9 squared. Now, when we multiply or square a square root, the answer is whatever the radical is. However, if we have a coefficient out front, we have to square that coefficient separately and then multiply the two things together. So just as some side work here, if I do 3 squared, I'm going to get 9. And then when I do the square root of 6 squared, I get 6. Okay, so when I multiply those together, 9 times 6, I end up with 54. Okay, equals 81. All right. So now when I subtract my 54, A equals 27. A squared equals 27. I forgot my square. There we go. And when we take the square root of A squared and 27, we get that A equals 3 times the square root of 3. Okay. Again, for those of you that need to see how I get 3 square root of 3, if I do my prime division, it's not an even number, so I can't divide by 2. I can divide by 3 and I'll get 9. I can divide by 3 again and get 3. So I have a pair of 3's and then one that's left inside. Okay. So I'm going to go through and highlight our solutions here. We have 10 on number 1. Our hypotenuse was 10 units long. On number 2, side A, leg A, was 9 units long. On number 3, our hypotenuse was 2 times the square root of 10 units long. And on number 4, our leg A was 3 times the square root of 3 units long. Okay. All right, guys, I hope you have a great day, and I will see y'all later. Bye.